The substitution rule is a method to compute antiderivatives. It is just an easy-to-use algorithm to make things a bit simpler and a bit more systematic than guess and check. In the next video, I will present a few examples of how to use it. However, in this video, I want to explain where the substitution rule comes from and why it works. As motivation, I will first investigate some examples by guess and check, then I will derive the general rule, and finally I will explain the notation that we commonly use. To begin, let's have a look at these two antiderivatives. First, I have the antiderivative of x to the 4 with respect to x. I know this is 1 over 5 times x to the 5 plus an integration constant. Why? We can check it. The derivative of 1 over 5 times x to the 5 is 1 over 5 times 5x to the 4, which is x to the 4, as I wanted. That's easy. Next, what is the antiderivative of ln x to the 4? Perhaps it is something like 1 over 5 ln x to the 5? We can check it. The derivative of 1 over 5 ln x to the 5 is 1 over 5 times 5 ln x to the 4 times 1 over x. Don't forget the chain rule. That's unfortunate. So this function is not an antiderivative of this function. However, if I had an extra 1 over x in the integrand, then it could be correct. The 1 over x was essential, again because of the chain rule. I can generalize this a bit more. What is an antiderivative of g of x to the 4 for any function g? Well, I don't know, but if instead I have g of x to the 4 times g prime of x, then an antiderivative is 1 over 5 times g of x to the 5. Why? Let's check it. The derivative of 1 over 5 times g of x to the 5 is 1 over 5 times 5 g of x to the 4 times g prime of x. Again, chain rule. And this will work for any function g as long as g is differentiable. Let's generalize it even more in the form of a nice theorem. If I know that an antiderivative of little f is big F, then what is an antiderivative of little f composed with g? I don't know. But an antiderivative of little f composed with g times g prime is big F composed with g. Why is that? The if part means that the derivative of big F is little f. The then part means that the derivative of big F composed with g is little f composed with g times g prime. Notice that the second statement follows directly from the chain rule plus the first statement. This is sometimes called the substitution rule, but I think it should be called the backwards chain rule. All I did is take the chain rule, which is a rule about derivatives, and reverse it to get a rule about antiderivatives. I used the chain rule backwards. To make this into a proper theorem, I should introduce my variables. Little f, g, and big F are functions, and I need to assume that big F and g are differentiable. And that's it. That's the substitution rule. This is the theory. In practice, we try to use this theorem in an efficient and algorithmic way that simplifies computation, rather than just guess and check. I will explain this next. Assume we know that an antiderivative of little f is big F, and we want to compute the integral of little f of g of x times g prime of x with respect to x. I want to think of g of x, the argument of little f, as the new variable. For that purpose, I will give it a name. I will call it u. Because I want to think that I am actually integrating f of u with respect to u. So I need to write here du. If I do this, it seems that I am rewriting g prime of x dx as du. This is what we call a substitution. U is g of x, and du is g prime of x dx. For now, this is just notation. There is a way to give a precise meaning to the differential and to make this rigorous, using so-called differential forms, but that is beyond the scope of this course, so I won't go there. I will just think of it as notation. Okay then, if I do this substitution, the integral becomes the integral of little f of u du. Now I find an antiderivative, which by assumption is big F of u plus an integration constant. And after integrating, I undo the substitution and I replace u back with g of x. The justification for this notation is that it gives us the right result. This is the same result I derived earlier. And the point of the notation is that it streamlines the process, so we don't have to use so much guess and check. This will become clearer with an example. Let's go back to the original example. I want to compute the integral of ln x to the 4 times 1 over x with respect to x. But this time I will do it using substitution. First, I notice that my function is written in terms of ln x, and that its derivative, 1 over x, is also here. This suggests I try the substitution u equals ln x. If I do that, I also need to substitute du as 1 over x dx. Great, this works because I already have 1 over x here. Then, this becomes the integral of u to the 4 du. I know how to do this. The answer is 1 over 5 times u to the 5 plus an integration constant. And now that I have completed the integration, I undo the substitution. And I am back to 1 over 5 times ln x to the 5 plus the integration constant. In general, every time the integrand is written in terms of a function, like ln x here, and the derivative is already in the integrand, 1 over x in this case, using a substitution like this is a good idea. And after doing the substitution, we hope to find an easier integral that we can complete. As to why the method works, that is the whole explanation I gave earlier. It all boils down to the chain rule. To make this clear, I should work through a few more examples next, and that is what I will do in the next video.